me this wonderful opportunity to present the recent results with Megumi Harada. So here's the outline for the talk. So briefly, we talk about the introduction to Newton-Okounkov body. So hopefully tomorrow there are at least 2 talks about Newton-Okounkov body, and you will see the details more. But namely, I will just say why we care about this. And secondly, then why do we care about Bott-Samelson variety as well? And so finally, let's construct a Newton-Okounkov body of Bott-Samelson variety. And we see some connections to sugar varieties and other toric degenerations. So this diagram describes this fundamental idea of this approach. So say A is your main object to study, then we assign some combinatorial objects to A and do some combinatorial things and try to get some information about our original A back. So this problem is sometimes called the lifting problem. So the most famous example for this approach is the toric geometry. So for the toric geometry, A is a toric variety with a given Cartier divisor. Then we can assign the Newton polytope to this Cartier divisor. And it is very well known that there is a very good dictionary from the polytope to divisor back. And I just want to introduce tropical geometry because this one also has the same idea. So here A is a very affine variety. That is to say, it's a sub-variety of an algebraic torus. And here, so-called tropicalization, we attach a certain weighted balanced fan to A, and it has been actively researched to get some application for the lifting problems. And now here's the talk, the main topic for my talk, Newton-Okounkov body theory. So here A is either a affine semigroup or algebra or linear series on variety, and we will assign a convex set. Most of the cases we will get compact convex set, and it's called a convex body. So the motivation came from the representation theory of reductive algebraic groups. However, Khovanskii and Lazarus-Feld-Mustata developed the theory for cases where you don't need group actions. Here just a few applications. So Khovanskii found proved for a large class of graded algebra, the Hilbert functions have polynomial growth. Also, they proved that the growth coefficients for these Hilbert functions satisfy a Brun-Minkowski type inequality. And also, Lazarus-Feld-Mustata and Khovanskii generalized Fujita approximations for linear series of variety. And also, David Anderson showed that there exists a certain type of toric degeneration when you get a nice Newton-Okounkov bodies. Okay, so here's a simple definition of Newton-Okounkov body. Say we have a affine semigroup sitting in this upper half plane with non-negative forced coordinates. Then you just take the closed cone generated by the semigroup and intersect this with a certain hyperplane on level M. M is just the lattice of the group generated by S projected on the forced vector in this Z. So it is a convex set. So let me just tell you one case of the Newton-Okounkov body. Say let L, so suppose we have a line bundle on a projective variety over the field of complex numbers with dimension n. Well, what we just need is algebraically closed field with characteristic 0. Just for simplicity, we use C. Then we can consider the graded C algebra, which is the direct sum of the spaces of holomorphic sections. I'm sorry, not regular sections of the tensor product. Then we convert this graded C algebra to a certain affine semigroup with a given choice of valuations. So the valuation means you assign n+1 integers to each sections. So once we have a affine semigroup, you get the convex set. But in this situation, you always get a compact convex set, and it is called Newton-Okounkov body.
Can you explain the G of S in the top right?
So S is a affine semigroup. G of S is just the group generated by the affine semigroup. And so suppose M is now 1. So we just don't want to have an empty set. You have a cone, and if you see the level 1 not empty, you just take the hyperplane on the level 1. But maybe the is more sparse than that, then you take the index. But of course, by changing the lattice, you can always get just m equals 1, 2. Okay, now here's a brief introduction to Bott-Samelson variety. So it begins with a choice of sequence of simple roots of SL and C. Again, you can replace SL and C by any reductive algebraic group. So, and usually we denote this sequence by just the indices of the simple roots. For example, for SL3C, we choose alpha 1, alpha 2, alpha 1. Then the Bott-Samelson variety is the product of the minimal parabolic subgroups corresponding to the simple roots quotient out by the standard Bn action. So these are non-singular projective varieties of dimension n. So n is the number of simple roots we chose. And these are important tools in geometric representation theory. Originally, they are defined as the singularizations of Schubert varieties. And for example, these are used to prove the rational singularities of Schubert varieties. And so they have similar properties as Schubert varieties have. For example, they have an action of a Borel subgroup, and also the projective coordinate ring splits into certain generalized Dematsu modules. So Bott-Samelson variety is sort of like easy to work with because it has nice coordinate systems. So finally, we want to construct a Newton-Okounkov body of Bott-Samelson variety. In general, it's not easy. The computation of a Newton-Okounkov body is not a simple job. But we were optimistic because Bott-Samelson variety is combinatorial and algebraically somehow. It has nice structure. So first of all, we have to fix a line bundle on the Bott-Samelson variety. So that's denoted by L of M. So namely, it's the product of the minimal parabolic subgroups times the one-dimensional representation of Bn, such that each factor of Bn acts by these multiples of fundamental weights. So the idea is that we use a certain toric degeneration of this line bundle as well as Bott-Samelson variety, and we found a very explicit description of these degenerations. So the Bott-Samelson variety degenerate to a non-singular toric variety. In fact, it is a Bott tower. And we found the degenerated line bundle as the line bundle of a certain torus invariant divisor. Sorry, so I'm skipping all this explicit description of Dn and the fan defining this Bott tower. So this is a very natural expectation to see the Newton polytope of D as an Okounkov body of Bott-Samelson variety with this line bundle. And we claim that that should be true if the divisor D is base point free. Actually, another reason that I'm thankful for being here is that, so yesterday while talking to other people, I found that there was a problem with my proof. So it was a horrible night yesterday. I think everyone had such experience. But finally this morning I found, I'm sure, well, it was a really nice for me actually. I had more understanding about these Bott-Samelson varieties. But however, I want to have a confirmation from, at least from my collaborator. So I changed from theorem to claim. So still it's true. So there is a valuation such that the Newton-Okounkov body is the polytope, the Newton polytope of the toric variety. And I want to say this Newton polytope is very well known and very simple lattice polytope in this case, because it is base point free. And it is the twisted cube of the Bott tower, developed by Grusberg and Karlsson in symplectic geometric setting. So idea of proof, we construct a very nice family over C. So I just, there are lots of adjectives in this very nice family. So I just didn't write down. It means we found a faithfully flat family which is proper over C, such that the fibers over all non-zero complex numbers are isomorphic to each other. So for example, the fiber over 1 is actually the Bott-Samelson variety we are interested in. And the special fiber, the fiber over 0, is the non-singular toric variety. And the line bundle L restricted to the special fiber is of D, and line bundle restricted to this generic fiber is isomorphic to our line bundle LM. So what we are doing is we try to work with the two objects. So this is the original one we are interested in, Bott-Samelson variety. And here is a certain Bott tower. So let me use Bott tower. And then we construct a one-dimensional parameter family. So this is fiber over 1, this is fiber over 0. And everything is isomorphic except this special fiber. And also we construct a line bundle on top of this Z, which by restricting to each fiber, you get one for Bott-Samelson variety, the other for Bott tower. So what is that? So Pasquier constructed toric degeneration based on Grusberg and Karlsson's symplectic setting. So it is done by a deformation of the Borel subgroup action. So let's just go back to the definition of Bott-Samelson variety. So here the Borel groups act on each P2 and Pn just standard way. But now we just replace this action by a certain twisting. So there's a lambda, never used it, lambda. So this, so we choose one parameter subgroup of maximal torus, which is called lambda here, such that the pairing with all simple roots are certain just given positive integer. And now this lambda T of B1 of inverse is just inner automorphism by conjugation. So when T is 1, this just B1 inverse. And when T equals 0, this is nothing but the projection from B to the maximal torus. So similarly, we can define the line bundle over Z2. So again, we use this deformation of the Borel group. And good thing about, so because of this choice of one parameter subgroup, we can extend this action onto 0. Of course, we need to say this more precisely in terms of algebraic geometry setting, but So I would like to skip it. So here, so this is one parameter, sorry. This is family over C. So before going to think about a choice of valuations to get these values, so what we are trying to do here is we actually want to get the values for BT and values for BSI. And if we know the numbers are different, then it's not optimistic. We want to show that these numbers we are finding from Bott tower is exactly the same as the values we are finding on Bott-Samelson variety. So it is well known that the dimensions of this. I'm sorry, I think that's mine.
It's yours.
Oh my gosh, I never got a phone call because that was my.
At least it's yours.
Oh my gosh, never got a phone call. Oh my gosh. Anyway, please don't call me. Oh my gosh. Because I just borrowed it from my father, and who will call me anyway? I think so. Yes. So again, the dimensions of these holomorphic sections is actually the number of values. So we want to show that, and in standard fact in algebraic geometry, there is a semi-continuity, upper semi-continuity of these dimensions of this space of sections. So the dimension of these sections at the special fiber may jump up, and we have to prove that that doesn't happen here. If we jump up on the special fiber, we get more values. So obviously the semigroups cannot be equal to each other. So we prove this constancy of these dimensions along the fibers using standard monomial theory and representation theory developed by Laksimbai, Littleman, and Magyar. And on the other side, we use toric geometry. So namely, we get a bijection from the in lattice points on this Newton polytope, which is the dimension of the sections on the special fiber. And so here, the number of lattice points is the dimension for the special section. And there is a so-called the set of standard tableau on Bott-Samelson. And they are certain bases of these holomorphic sections on the Bott-Samelson variety. And we managed to get a bijection if T is base point free. Well, I should say that this condition is not the optimal one. So I'm still looking for a better condition. Anyway, so now we make sure the number of values we are getting on these two computations are equal to each other. And now, so what we have to do is to say we get a section on this line bundle with the valuation. Say, then I have to show that there exists section on Bott-Samelson variety, which has so this is for 0 fiber, this is for the fiber over 1. It's the same. So if you get values on this side, we prove there is a section here which has the same values. And again, by the so the semigroup should be, these two semigroups are equal to each other. Again, because of this constancy of the dimensions along the fiber, it is again a general fact in algebraic geometry. You can always extend section on the spatial fiber in a neighborhood of this fiber. However, for us, except the spatial fiber, everything is isomorphic to each other. So you can extend F to all over. But that's not it. What we really need is that we have to show there is extension which preserves this valuation. So I didn't tell you what is the valuation yet. So to get these nice valuations, the idea is that we get a nice local coordinate system for each fiber by embedding n+1 dimensional affine space with these coordinates tx1 up to xn. So what I'm doing is that we embed, so Cn plus 1, remember each one has n dimension, and nicely means each fiber gives you Cn affine open subset. And on this Bott-Samelson level, this is actually given by a certain maximal open cone in this toric variety. And there is a boundary divisor. And this, the D is actually support
over 2
boundary. So it doesn't intersect with this open subset. So here there's it is already shown in the Lazarsfeld and Stata's paper. If you have such a situation, you can always realize the Newton polytope of D as the Newton Okounkov body for this toric variety. So here's the valuation we are choosing. So for each fiber, we take the lowest term valuation with respect to this term order. So xn is greater than xn minus 1 to x1. What I mean by this lowest term valuation is that any section on the fiber can be represented as a Laurent polynomial in these variables x1 to xn. And you just take this lowest term with respect to this term order and take this exponent vector. So that is the valuation we are taking. So you may wonder why we choose this somehow reversed order. So that's because, again, we embedded this affine open subset nicely such that it behaves well with our line bundle. And there is a natural closed immersion on the level of Z, and as well as on the level of line bundle. So it is somehow, so on the Bott-Samelson level, the bottom is trivial and actually doesn't really have to be in this order. But for line bundle L, we had some kind of twisting. So only I shouldn't say only, this choice, L of Mn included, so there is a natural embedding to L of Mn minus 1, to Mn. So there's an inductive process to come up with this extension F tilde, which has this, so this lowest term valuation can be identified with this valuation given by vanishing order along this coordinate system. Xn is 0, xn minus 1 is 0, 2. So because of this natural closed immersions on both levels, we can cook up F tilde, which preserves this vanishing order by induction. So here are some examples with also the connections to Schubert varieties. So again, we choose alpha 1 alpha to alpha 1. Then this is reduced with compositions. So there is a birational morphism to the Schubert variety. And in this case, it is whole Fleck variety. So this polytope is for L011, which is the pullback of the line bundle on the flag variety with the weight alpha 1 plus alpha 2. But these are not base point free in this case, so we can apply our claim in this case. And please notice that this one is not a lattice polytope. It has one vertex with rational coordinates. But this one doesn't really rule out the possibility that this one can be realized as the Newton-Okounkov body, right? However, if I just take the lattice points of the previous polytope and take the convex hull, actually this is the string polytope you can find in Kaveh's paper, where there's slight rotation here. And then Kaveh showed that this is a Newton-Okounkov body of Bott-Samelson or Schubert variety. And in the Newton-Okounkov body theory, the volume of this polytope is equal to the degree of this line bundle embedded into the projective variety. So that, when I say volume, I'm taking the integral volume. So this one is bigger than that. So this one cannot be Newton-Okounkov body of any valuation, because this one has a larger volume, doesn't match with the volume. So this example shows that this PD, the special case of a twisted cube, is also, I'm expecting to find a nice relation to the string polytope. And so this is for L111. So this line bundle is not the pullback of any line bundle on Schubert variety. So you have to tensor with something else. Now D is base point free but not ample. So the polytope is in blue. So this one is a Newton-Okounkov body of Bott-Samelson variety. So let me just erase that. And as you see, there is a singular vertex. So if you consider the toric variety corresponding to this one, it still has a singularity. So let's try one more. So L is 211, then D is ample, and furthermore, the polytope is smooth. And the outer normal fan of this red polytope is the fan constructing the Bott tower. So in fact, the proof shows more than just saying that the Newton-Okounkov body of Bott-Samelson variety is the Newton polytope of PD. We prove that these two semigroups are equal to each other. But the semigroup we construct on this special fiber is finitely generated by degree 1, namely the lattice point of this polytope PD gives you the generators. So we have the semigroup of the Bott-Samelson varieties finite generated 1. And David Anderson said in this case, there exists a toric degeneration of Bott-Samelson variety with LM very ample line bundle. So it's a natural question of how are they related. I mean, Pascal's toric degeneration and David Anderson's toric degeneration. So just we are still work in progress. But just to say one thing is Anderson's toric degeneration somehow extrinsic. This all toric degeneration is in certain, in this case, it's in the projective space. So it's somehow they use a Rees algebra to find one particular family. And as you saw, the Pascal's degeneration is intrinsic. It doesn't come with any any projective embedding. But I expect that they are closely related. Okay, that's it.